Last episode ended right here. Proof assistants run on CIC, COC plus a universe hierarchy plus inductive types. We sketched each of those three pieces, but inductive types stayed as just a name on the board. The part where a proof assistant actually builds its data. Today we open it. Constructors and eliminators are how any type in type theory is defined. One side builds values, the other takes them apart. What makes a type inductive is that you only declare the constructors and the eliminator comes back for free. We'll see what that looks like for pairs, sums, booleans, and numbers. And recursion and induction will follow. Start with the simplest example we already know. The product type, A times B. One constructor, as the pair, AB, builds a value. Two eliminators, the projections FST and SND, pull it back apart. Suppose we want a pair that holds a number and a list and forces the number to match the list's length. A plain product won't do. Nothing stops us from pairing 5 with the 3-element list. What we need is a pair where the second slot's type can refer to the first slot's value. That is the dependent pair, written with a capital sigma. Pick a length n, then pick a vector of exactly that length. The mismatched pair on the right doesn't type check. Same template. One constructor, two eliminators. The constructor takes an A together with a B whose type is B applied to that specific A-ris. The eliminators are still FS and S and D, but now S and D's type literally depends on what FST returns. Swap BX for a proposition pi and x. Again, and S has the existential quantifier. A proof of there exists an x such that px is just a SE value, a concrete witness, paired with a proof that the predicate holds for it. In Lean, the proof is literally a pair, the witness 2 on the left, and on the right, a certificate that it satisfies the predicate. A proof and a piece of data share the same shape. That's the whole point. The coproduct, more often called the sum type, holds a value that is either an A or AB, tagged with which side it came from. This time there are two constructors. INL wraps an A, INR wraps a B. And the eliminator changes shape too. To use a value, you can't peek inside until you know which constructor built it. So you supply one answer per case. Concretely, hand the eliminator a function from A to some target C and a function from B to the same C. The two combine into a single function from A Pilates B to C. Through Curry-Howard, this is the logical OR. Just as A and B lined up with the product last time, A or B lines up with the sum. Proof is either a proof of A wrapped in INL or a proof of B wrapped in E and R, and the eliminator forces you to handle both cases. Booleans fit the coproduct template. Two constructors. The only difference from A plus B is that the constructors carry no payload. The single bit of information is the choice of constructor, and the eliminator is the case split you've been writing your whole life. If, then, else. One answer for true, one answer for false, and it picks the right one. Step back for a moment. Fast and sand on a pair, the case split on a sum, if, then an else on a bool. They all share one shape. The eliminator of a type with multiple constructors is pattern matching. One clause per constructor, every clause returning a value of the same type. In Lean, this is the syntax, one arm of the match for each way the value could have been built. The natural numbers fit the same template, but with a twist, the second constructor is recursive. Suck takes a gnat and hands you back another gnat. Apply suck to 0 over and over, and you walk through every natural number. Hey. Pattern matching looks the same, one clause per constructor. But the sucks branch hands you back a k that is itself a gnat. To say anything useful about sucks quo, we usually need the answer for k first. We need to recurse. The eliminator that captures this is called the recursor. Hand it the answer for 0 plus a rule that turns the answer for k into the answer for suck kauli, and it gives you back the answer for every n. And just like every eliminator before it, the recursor is derived from the shape of the constructors alone. The kernel needs nothing more. When P returns a type, the recursor builds a function. When P returns a proposition, the exact same recursor builds a proof for every n, evidence that Pn holds. That second reading is exactly what we call induction. Here's the proof from the previous episode, and the structure is no accident anymore. One branch for 0, one branch for suck chi with an inductive hypothesis, yash in scope. The exact shape of Nat's constructors read in prop. One last surprising case. In Martin-Löf type theory, mark the lineage agda follows, equality itself is an inductive type. A single constructor, Riefel, builds a proof that AI equals itself. EQ of A is a family of propositions, one for every possible right-hand side, and Riefel only inhabits the diagonal, the case where the two sides are the same. The recursor that falls out, historically called J, says this. To prove anything about an arbitrary equality proof, it suffices to prove it for the canonical Riefel case. Substitution, symmetry, transitivity. Every rule of equality reasoning you've ever used derives from that one principle. From a single constructor, an entire logic. Whenever you declare an inductive type, S, sum, bool, nat, list, tree, and as we just saw, equality itself, the kernel hands back pattern matching, the recursor, and the induction principle. We just built the recursor for nat by hand. Now let's see what user-level match is doing on top of it. A match is only half the picture. It analyzes a constructor but can't call itself. Lean closes the gap by leaning on the recursor we already have. When you write a recursive df, the elaborator quietly takes every match together with its recursive calls and rewrites them as a single application of the types res, the exact one we just built. No new keyword needed at the surface. Rock takes a slightly different route. There, the recursive self-call is its own kernel-level operator called fix. Pair fix with match, and you get exactly the two pieces the recursor packs into one. a base case for 0, and a step case that already has the answer for k. Different layering, same destination. Rocks match and fix together, do what Lean's recursor does in one move. Strict syntactic checks on each side mirror what Reckitt's type would have demanded. Here is the interesting point. When the function's return type changes per branch, the 0 arm returns something of type P0, the Suxquan arm something of type P Suquegi. That P you just wrote is what the recursor calls the motive. Its very first argument, pi nat type. The function telling each branch what type it should return. Ordinary recursion is the case where Pn is the same type for every n. Dependent recursion is what happens when Pn genuinely varies. The recursor swallows both in one shape. Where the two systems part is how that motive gets into the kernel. Rock makes you spell it out. Every dependent match carries a return clause where the motive lives literally inside the syntax. Here, as nya return p and zeroast tells the kernel exactly what each branch should produce. Lean usually lets you skip the annotation. No return clause, no motive. The elaborator looks at the surrounding type, sees Pn in the signature, and synthesizes the motive on its own. Only when that inference fails does Lean ask you to write match n with motive, P, by hand. We started today with this formula. Now the unopened box is open. Every data type in a proof assistant, and every proof by cases or by induction over one, flows through the same constructor and eliminator template. One piece we left closed, the CCO on the left. The subscript O stands for a whole infinite hierarchy of universes, and that hierarchy is what keeps the system from running into Russell-style paradoxes. We brushed past it today, but it has its own story, a tour for another time. Thanks for watching.